Oh, okay. So excellent. We've started recording. So thank you very much, Rajesh. And so I'll repeat, welcome everyone to the fourth lecture. This is going to be my last lecture. And today I'm going to present from slides because some of the material that I have is not going to fit very comfortably into the small blackboard that you see behind me. Okay, so that's the reason we are doing it this way. So let's go on. Let's carry on. Okay, so where were we last time? We had characterized all finite dimensional R linear spaces that admit at least one almost complex structure. Remember that the characterization is simply on dimension. The necessary and sufficient condition for an R linear space of finite dimension to admit at least one almost complex structure, that it be even dimensional. And so now that we have been able to identify R linear spaces that admit some almost complex structure, we had begun to admit the question, how can I account for the entire collection of almost complex structures? Presumably there is more than one, right? And you know that there are, at least on the face of it, many almost complex structures owing to a problem that I had given you in the first problem sheet, which is that if I have an almost complex structure, which is a certain real isomorphism of V, then any conjugation of it by GL of V gives me another almost complex structure. But this question, given an R linear space of even dimension, how do we account for all? The key thing is distinct almost complex structures needs a little bit of work, because even though we have that situation of the conjugacy action on the space of all almost complex structures, the question is, if you take an almost complex structure and then you conjugate it by an element of GL of V, do we necessarily get another complex structure? And so that led us to the consideration of this object, which is you fix an almost complex structure J0. So I call this set S sub J0 to be the set of all those elements in GL of V, in other words, invertible R linear transformations of V, which conjugate J0 to itself. And in fact, this set is, we gave a description of this set on the nose. This set literally is what I just highlighted. And for this, I need to fix an ordered basis, fix a certain ordered basis, so that the matrix representation of J0 has a special form. It has this anti-diagonal forms, with the anti-diagonal terms being the matrix minus 1 sub n and 1 sub n. So the description is literally that S sub J0, this thing, is the collection of all invertible matrices, invertible linear transformations, such that the matrix representation with respect to this special basis has this form, has this special form or special block form. Okay, so that's what we saw last time. So remember, this question that I have in italics is not a question that we have answered fully, because the question, you cannot simply say, well, the set of all distinct almost complex structures is in one-to-one correspondence with GL of V, because this set is non-trivial. So let's carry on. And here is the theorem. Here is the theorem that addresses addresses the question on the previous slide. So once again, you take an R-linear space V and you fix it. This is a space of even dimension. Let's call that 2n. And let us denote by this notation AC of V. Let's denote this as the set of all almost complex structures in V. Okay, so to be able to describe all distinct almost complex structures, we take our cue from what we had in the previous slide, which is we are going to fix some almost complex structure J0. And the set that I had in the previous slide, this set, I'm going to give it a name that is more familiar from the point of view of group actions. So I'm going to call stabilizer sub GL of V of J0. Let this notation denote the stabilizer of J0 under the conjugacy action of GL of V on the space of all complex structures. But this is just in group theoretic notation. This is simply this set itself. Please note that this is a collection of invertible linear transformations. But now when I identify this as the stabilizer, you realize that the stabilizer is a subgroup of GL of V. Then, here is the theorem. Then, the space of the set of all almost complex structures is in one-to-one correspondence with this. What is this object? Let's remind ourselves of some group theoretic notation. What I just highlighted is the collection of all cosets, all right cosets, as a matter of fact, of this stabilizer subgroup in the group GL of V. And then I can give an even more explicit definition. It is the above collection of all cosets is the collection of all cosets in GL of V of the subset defined in this way. This is the subset of all invertible R-linear transformations of V, such that the matrix representation with respect to a special basis, and I'll tell you what the special basis is, I've already told you earlier, has this very special block form. And so what is the special basis? It is that special basis that I have talked about, such that J0 has the standard antidiagonal form. So note there is a one-to-one correspondence with something that is new to us, with something that is a whole lot familiar. So let's look at the proof. So I'm going to draw upon basically something you do in a first course in abstract algebra, if that course involves the basics of group actions. So remember, I remind you again that this is just my short form for the set of all almost complex structures in V. We've seen in a homework problem that GL of V acts on this set by conjugacy, but we've actually seen a lot more in that problem. But I will remind you in a couple of minutes what more we have seen. Okay, so what I'm going to do is I'm going to look at the orbit of J0 under the conjugacy action of GL of V on the set of all almost complex structures. Now, why I do this is because then there is this basic 6 or 7 line proof in group theory. In basic theory of groups, action says that consider this function. So inside of this orbit, you pick your favorite J and map it to this particular right coset of the stabilizer subgroup of J0. This is the coset by an invertible linear transformation S sub J, where S sub J is such that S sub J inverse composed with J0 composed with S sub J is equal to J. In other words, S sub J conjugates our J naught to J. But why should there be only one S sub J? Well, that is the thing that we learn in the theory of group actions, right? That this is a genuine map. This is a genuine function. In other words, it is well defined. If I had a different J which did this, I would still have the same coset. So in fact, this function is well defined and bijective. So we have this from group theory. And now I actually want to talk about, so what we have established is at least the orbit of J naught is in one-to-one correspondence with the set of all right cosets of the stabilizer subgroup in GL of V. But now I want to remind you of that problem in the assignment. This is problem number 5, sorry. You see, what that problem says is, given any two almost complex structures, J1 and J2 on V, there is an S in GL of V that conjugates J1 to J2. So you see, you take any two complex structures, almost complex structures, one is related to the other by a conjugacy. So in short, the orbit is the whole of the space of almost complex structures. You see that? So in other words, well, how, again, let's repeat that. How do we get this conclusion? You pick any almost complex structure, and then, of course, I have fixed an almost complex structure, J naught. My homework problem tells me that the one that you have picked is linked to the J naught that I have highlighted by a conjugacy. So therefore, the orbit is actually all of the set of almost complex structures. And so we are done. So when I now, so what do I mean by star? So let's look at what star is. Let's go back to the previous slide. So star is this problem we had solved in the last 15 minutes of the previous lecture. So this was an actual stabilizer computation. So that's what I mean by star. So this statement transforms to the space of all almost complex structures is in one-to-one correspondence with the set of cosets. But star gives us an exact stabilizer computation, and that gives us this last line. So the set of all almost complex structures, we are able to parametrize this, and in fact, we have a canonical parametrization. The canonical parametrization is this map by the set of right cosets inside of a familiar group, the subgroup being explicitly given. So that is our theorem. So I am, in fact, going to now transition to a very different topic. So before we do that, any questions? Any questions so far? So you will have to do the following. I might not be able to see your hand raised. So you'll have to ask to be unmuted. Any questions? Okay, so no questions. So, well, let's take a few more minutes before we proceed to a completely different problem. So you might ask, well, why are we interested in almost complex structures? Well, they are interesting in their own right, in that they are a class of invertible R linear transformations which happen by another problem that I had stated in the first problem set, and which in fact I had solved partially in the tutorial. An almost complex structure mediates between a R-linear space and a canonical uh, complex complex vector space. So given an R-linear space that admits an almost complex structure, the same set. So I take the R-linear space and I consider it now as a set. In fact, I consider it now as an abelian group with respect to the addition operation. And I can, depending on the almost complex structure, define a new complex scalar multiplication, so with which, by means of which, a given pair of a real linear space and an almost complex structure upon it, there is a canonically associated complex linear space. Now, this is actually significant just outside, far beyond the scope of linear algebra, since the focus of this workshop is linear algebra. I'm just going to spend a couple of minutes. I'm not going to elaborate any further. And the question is this. If I give you a smooth compact manifold, a smooth compact classical manifold, that is a smooth compact real manifold, then can I impose upon this smooth object a complex atlas, a holomorphic atlas? So those of you who know manifolds, you know what an atlas is. A complex atlas is a similar object, except that the transition homomorphisms the transition functions are not just diffeomorphisms, but they are one-to-one and onto holomorphic maps. In other words, they are biholomorphisms. So the question is, if you have a classical compact complex manifold, classical compact smooth real manifold, can you endow it with a complex structure? Can you endow it with a complex atlas? Now, the reason why this question is a salient one is, if you are in real dimension 2, this answer is exactly no. And the answer is if and only if the underlying smooth manifold is oriental. So the question is a meaningful one. And then the question is even more meaningful. Given a real manifold of a fixed topological type, how many different inequivalent complex structures can we endow the real manifold with? And this is again a meaningful question, because some of you will know, if I just take a torus, this is a perfectly nice real two-dimensional compact manifold, and you can endow the same real object with uncountably many inequivalent complex atlases. So the second part of the question is also meaningful. And then if we go outside of real two dimensions, so as I said, in real two dimensions, the problem is completely solved. If we go to higher dimensions, the first thing you will realize that if an underlying real compact manifold must admit a complex atlas, then you see that object will have to be of even real dimension. So do you see its resemblance to this condition? Now, the question of then, first of all, endowing the given smooth manifold with a complex structure, whether there one even exists, is a hard one. So the way we do it is we go by what I call almost complex structures on a real even dimensional manifold. So that is the connection with this problem. Given a real manifold of even real dimension, an almost complex structure is a smooth assignment of an R-linear almost complex structure on each of the fibers of the tangent bundle. So if you have a smooth real manifold of dimension 2n, then its tangent bundle is, of course, double the real dimension, but each fiber is the prototype of each fiber is an R linear space V of dimension 2n. So an almost complex structure in geometry is a C infinity smooth assignment to each fiber of the tangent bundle of an almost complex structure, such that these almost complex structures vary C infinity smoothly. And there is a canonical prescription for determining when an almost complex structure, this time I don't mean a linear almost complex structure, but a complex structure on the real tangent bundle. So there is a standard prescription for determining, and it is if and only if determining when and only when such an almost complex structure gives you a genuine complex atlas on the even dimensional smooth manifold. Now, there is a prescription. I'm not saying it is easy to implement the prescription, but a prescription is there. So you see the question of determining whether a smooth real manifold admits a complex atlas. In higher dimensions, the way to address this question, because of this prescription, is to assign a smooth, almost complex structure on the tangent bundle. Now, for the same reason that on a fixed vector space, it is possible to find at least one almost complex structure. But also, you see, so you know the fibers of the tangent bundle are all real isomorphic to each other. So every fiber, this V stands as a prototype for every fiber. But in fact, we can vary a linear almost complex structure. And how many are there? This result one tells you they are aplenty. So it's enormously easier, given a compact C infinity smooth real manifold of even dimension, to find an almost complex structure, which I repeat, is an assignment fiber by fiber on the tangent bundle of a linear almost complex structure, which is what we studied. Okay. But because of this fact, on a given vector space, since there are almost linear, almost complex structures aplenty, the ability to construct an almost complex structure on a compact real manifold is a much easier thing. And then, since this is an easier thing, this is the problem we knock down. And then we hope we can put our hands on this prescription, which I will not tell you anything about, to determine whether or not a smooth manifold of even dimension has a complex atlas. So in 7 or 8 minutes, I have told you a certain story. This has got nothing to do with linear algebra, but this is really the one of the directions in which the study of real linear, almost complex structures that we spent 1.5 hours worth of lecturing studying. What I just described to you is probably the most important direction in which this particular theorem is taken. Okay, so time to change gears. I'm now going to, so for the next 1 hour, I'm going to switch to a very different problem. This is an unrelated problem, okay? So if you look at the material in lectures 1, 2, and 3, there is this common thread that's running through it, which is the problem of looking at an R linear transformation on an even dimensional vector space and trying to see when this linear transformation happens to also act C-linear, right? That problem gave us this operator J sub D, which happens to be just a prototype of this entire class of operators I have been talking about, called almost complex structures. This has got nothing to do with it. This is a problem that sits by itself in its own right. It is again a problem in complex analysis, but the solution to this problem is entirely parallel to an associated problem on Hermitian matrices. Okay. So the problem is this Pick interpolation problem. Let me quickly define this problem. I'm going to define this problem in great generality, and then I'm going to say that, well, in this generality, it's difficult to even address this problem. But the problem in general, this is called the Pick interpolation problem. So I'm going to refer to it by the short form PI. So I have two domains, omega-1 and omega-2, sitting in complex Euclidean spaces, not necessarily of the same dimension. I have m distinct points. Distinct is important. We will see later. M distinct points in the first domain, in omega-1, and we have m points, not necessarily distinct, but if they are not distinct, then the points W1 through Wm are repeated according to multiplicity in the second domain, omega-2. So given these two domains and given a set of m distinct points and another set of m points may be repeated according to multiplicity, find a necessary and sufficient condition on the pairs Z1, W1, Z1, Z2, W2, dot, 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 Zm, Wm, such that there exists a complex analytic map, or there exists a holomorphic map, F from omega-1 to omega-2, satisfying f of Zj is equal to Wj for each j. So, stated in this generality, the problem is pretty much intractable. So in practice, the problem PI is stated for various choices of pairs of domains omega-1 and omega-2. So this actually turns out to be a problem of considerable interest even outside of complex analysis. So two things. I really don't have the time to go into what outside of the realm of complex analysis makes people care about this problem PI. So I'm just going to state this fact, and I'm not going to dwell on it. But the other thing is I shall focus only on the case where omega-1 is equal to omega-2 is equal to D, the open unit disk. Now, even in this case, this problem is highly non-trivial because of the following reason. You see, your source domain omega-1 is the open unit disk. Now, if you, let's just consider a very simple problem of Z1 and Z2. Okay. Then if W1 and W2 were in the open unit disk, and you were allowed to find a holomorphic map taking values in C, then this is a totally trivial problem. You can explicitly write down by hand, in fact, a polynomial that will carry Z1 to W1 and Z2 to W2, but there's absolutely no guarantee that the image of the open unit disk under this polynomial will sit inside the open unit disk. There is no guarantee. Secondly, very often, just given Z1, Z2, and W1, W2, so just given this pair of data, you see, if you have a holomorphic map from the open unit disk to the open unit disk, then the locations of W1 and W2 with respect to Z1 and Z2 are constrained because of the Schwarz-Pick lemma. So clearly the Schwarz-Pick lemma tells me that if I pick Z1 and Z2 distinct, I can't just pick W1 and W2 and hope to find a holomorphic map satisfying the property that I just highlighted. Okay, so this is a genuine problem. This is even for the case omega-1 is equal to omega-2 is equal to D, this is a genuine problem. There's some disturbance that I just heard. I wanted to ask you, am I audible to you? Do I continue to be audible to you?
Yes, sir.
Okay, thank you very much. Okay, so the classical pick interpolation problem is the problem where omega-1 and omega-2 are both the open unit disk. So let's rephrase the problem. You are given distinct points Z1, Z2, dot, 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 Zm in the open unit disk, and these are distinct, and you have points W1 through Wm also in the open unit disk. In this case, they need not necessarily be distinct, but they will have to be repeated according to multiplicity in the latter case. Hello, is that a question? Okay. So the question is, can one tell simply by examining the points that were given to me whether there exists a complex analytic map from the open unit disk? And this is important. The image must also lie in the open unit disk such that Zj is mapped to Wj. This is our problem. And the answer to this question, at least in the classical case, is yes. And there is this extremely beautiful theorem proved independently by Georg Pick and Rolf Neven-Linne. So when I mentioned Pick interpolation, when I mentioned the Schwarz-Pick lemma, the Pick in Schwarz-Pick is the same, very same Pick. So again, we have the data that as above, Z1, Z2, dot, 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 Zm are distinct points, W1 through Wm, M points repeated according to multiplicity. They are allowed to be repeated according to multiplicity. These are sets of points, lists of points lying in the open unit disk. Now, there exists a holomorphic map from the open unit disk to itself, call it F, such that f of Zj is equal to Wj for all j, provided this matrix. So you see, this matrix is given only by the points you have given me. The matrix, the jkth entry of this matrix is given by 1 minus wk conjugate times wj, this whole thing divided by 1 minus zk conjugate times zj. If so, this is an if and only if condition, if and only if this matrix is positive, semi-definite. So this is the theorem, and this is the theorem that we shall be trying to prove today. So I hope by seeing this and this notion of positive semi-definiteness, you see the connection with linear algebra. In fact, the way this problem will be solved, I'm actually going to go through the complex analysis rather rapidly. And I'm going to make an observation that the complex analytic problem is entirely parallel with a problem on positive semi-definite quadratic forms. And you put the two together, and that's how this problem is solved. So before we try to prove this, the question will arise, the condition that guarantees that there exists a holomorphic map with a desired property. The condition is so far removed from anything in complex analysis. So how do we even see this? So that's what we should try to understand first. So let's try to understand the proof in the n equals 2 case. Okay, so it's kind of tiresome because there are so many subscripts involved to keep saying f of z sub j is equal to w sub j. So I'm going to use the expression f interpolates the given. So when I speak, I'm going to say f interpolates the given data. And in writing, you will see on my slides, f interpolates the collection of pairs Z1W1, Z2W2, dot, 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 ZMWM. Okay, so that's just some words. So let me give you some notation. So script B is the set of all holomorphic maps on the open unit disk whose image is contained in the closure of the closed unit disk. Now, psi sub A is something everybody recognizes, right? Psi sub A is in fact a very specific disk homomorphism. So this is the map that maps Z2. So I've written this in functional notation. Okay, so this dot over here means A conjugate multiplied by the variable. So this is the map that carries Z2, the Navier transformation, Z minus A divided by 1 minus A conjugate Z. In particular, this is an automorphism of the disk that maps A to the origin. So this is going to be important. Keep in mind what this does. Okay, so now, if there is a holomorphic map that carries Z1 to W1 and Z2 to W2, then the quantity, the modulus of W2 minus W1 divided by 1 minus W1 conjugate W2, this absolute value, because I'm observing that I am assuming that f of Z1 is W1 and f of Z2 is W2, this is exactly equal to the middle term that I have written. And you see the Schwarzschild lemma says that this middle term is less than or equal to the modulus of Z2 minus Z1 upon 1 minus Z1 conjugate times Z2. Okay, so I have this implication. If f interpolates this data of sets of 2 points, then the following inequality follows. Keep it there for the moment. Okay, I want to show that the converse is also true. All right, and then I will go to the problem with matrices. So just for better visibility, little zj and little wj don't look very clear in a drawing. So where in the drawing, in the next slide, I'm going to depict little zj by big aj, and I'm going to depict little wj by big bj. So let's get on with it. So here is the drawing. So this time I'm going to assume the inequality, okay, that mod of W1, W2 minus W1 over 1 minus W1 conjugate times W2 is less than the corresponding mod of the corresponding ratio for Z1, Z2. And notice my change in notation. So Z's become A's and W's become B's. Okay, so suppose I have this inequality. So you have on the left, this is a picture of an open unit disk. You have A1, and then this red point represents my A2. Okay, so what I do is I switch on the Möbius transformation psi sub A1. Remember what it does? It is that disk automorphism that transforms A1 to the origin. So you see this fat black dot that I have just highlighted, it moves to the origin. And this red dot, well, it goes wherever it'll go. But do you see the length of the radial segment joining the origin to this red dot, which is the image of, this is the image of A2 under the map psi sub A1. So the length of this green line is exactly R of A, which I have defined at the top of the picture. Okay. Now I carry out the same operation on the target disk. So you see our target data are B1 and B2. So B1 I have identified as a black dot, and the blue dot denotes B2. I switch on the disk automorphism B, psi sub B1, which you remember was going to carry this black dot to the black dot I just now outlined. So the blue dot, well, it's going to go wherever the hell it goes, but the modulus of the image or the length of this red line segment, this red radial segment that I drew, is precisely R sub B. So you see, what am I assuming? I'm assuming that R of B is less than or equal to R of A. So you see, R of B and R of A have geometrical interpretations, although I had started out with an assumption which is an inequality. R of B and R of A, the left-hand side and the right-hand side happen to have geometrical interpretations. Now, you see, I can easily find a holomorphic map from the open unit disk to itself that carries the red dot to the blue dot and the black dot to the black dot. Well, the black dot is just the origin in both of the pictures, right? And this map is, you see, what I do is I take a dilation factor, and the dilation factor is the ratio R of B divided by R of A. Okay. So my map is simply psi going to psi just a minute. Are you being able to see all of the 4 disks?
Yes, sir.
Okay, somehow my graphic is freezing up. Just give me a sec. Maybe my internet connection has become unstable. So let me try this again. Let me try this once more. Right. So what is this psi over here, right? Let's understand. Hopefully, when I advance the slide this time, I will have no problems. Yes. So you see, the red dot and the blue dot, they may have different arguments. So this psi is a rotation. It is e to the I theta, where theta is that theta Well, let's do it one step at a time. So I have a map that is going to map the open unit disk to itself and will map the red dot to the blue dot and map the origin to the origin. And how is that going to work? I first switch on the dilation by this factor that I have just highlighted. You see, the very fact that R of B is less than or equal to R of A implies that this dilation factor is less than or equal to 1. So this dilation map, that is to say, Z being mapped to R of B divided by R of A times Z, will map the open unit disk to the open unit disk. What this dilation factor will also do is the length of this green line will shrink and match the length of this red line. And then what I do is I switch on this rotation. I switch on an e to the I theta. So I have a dilation composed by a rotation, which will do the job. So you see now, if you do this traversal, if you go from this disk to this disk, then you apply the map that I have explicitly written, going from the upper disk to the lower disk, and then go inverse, which is the formula I wrote down. It will have to map the black dot to the black dot and map the red dot to the blue dot. In other words, given this, I have cooked up for you an explicit F that does the job. So let me pause for a moment. So does everyone see this? Do you understand this point? Any doubts at this point? Okay, if not, then let's carry on. So you see, I haven't actually proved the theorem by Pick and Neven-Lindner in the m equal to 2 case. I have actually proved some other result. I have shown that this inequality is necessary and sufficient for the existence of an F that interpolates this data comprising of 2 pairs. Right. So I just wrote down what I say. So we have just shown this part. Now, so you see this condition that I wrote up here, it is equivalent to this inequality that I just wrote. How so? If I multiply both sides by a minus sign, the inequality is reversed. Then if I add, next I add 1 on both sides, then the reversed inequality continues to hold. And then when I simplify and rearrange terms, I get this, okay? So that's how dot gives us this new form. But this new form is actually familiar if you're familiar with a certain category of quadratic forms. This inequality just happens to be the determinant of this 2 by 2 matrix. All right? In other words, I have shown that the 2 by 2 principal minor of this 2 by 2 matrix is non-negative. But if you look at now the two 1 by 1 principal minors, they are already non-negative because mod of each wk and the mod of each zj is less than 1. So what did I just establish? I established that the inequality given by this red dot is equivalent to the positive semi-definiteness of this matrix. How so? By showing that all possible principal minors are non-negative. And so you see, we've established the proof of the Pick-Neven-Lindner problem in the case n equal to 2. So that's how we do it. So do you see the structure of this proof? What I just did is I first solved a problem that involved a certain inequality, which was a purely complex analytic if and only if. And then I showed that this if and only if can be rephrased in matricial terms. So there's this 2-step process. So this two-step process actually also lives for the, so the guess as to how this positive definiteness of a certain Hermitian matrix is involved comes through the analysis of the m equal to 2 case. And you see why the statement in matricial terms, you see this condition is kind of very special to 2 points. This is not a condition that's generalizable to more points. So do you see this theme in a lot of my lectures? I write something and then I rewrite the same thing in another way, and this other way happens to be generalizable. So this positivity condition is generalizable to more points, okay? So that is at the root of the conjecture, and what Pick and Nevenliner showed independently, that the conjecture is true. So let's just look at the classical Schwarz lemma. Everyone knows this. It has been, I put this up on this box here. I'm going to go through the slide fairly rapidly because I want to get back to linear algebra as soon as I can. Now, this Schwarz lemma that everybody is familiar with, it gives us a trick to reduce the given Pick interpolation problem to an equivalent problem involving 2 distinct points in the domain and 2 points in the target. How is it done? So suppose you are given this data Z1 through Wn, Z1 through Zm and W1 through Wn. Then there exists a capital F in the function class that I talked about that interpolates the data that we have if and only if there is a different function in the same class called f tilde that interpolates this new, more complicated looking data. Z1 W1 is replaced by psi sub Zn acting on Z1, and the W1 is replaced by psi sub Wm acting on W1. Z1, Z2 W2 will be replaced analogously. Let's look at what the m minus first pair is replaced by. Well, the Z sub m minus 1 is replaced by the action of this disk automorphism on Z sub m minus 1, and Wm minus 1 is replaced by this disk automorphism acting on W sub m minus 1. But now remember, psi sub Zm is that disk automorphism that maps Z sub m to 0. And this psi sub Wm is that disk automorphism that maps W sub m to 0. So you see, that is why this last pair becomes 0, 0. So the way to coherently describe this new list of pairs of points is that the first entry in each pair is being acted upon by psi sub Zm, and the second entry is being acted upon by psi sub Wm. So this is now clear, because if there exists a Z that does this that I have highlighted, then what you do is to get an F tilde that does the needful. You compose F on the left. Sorry, I always get my left and right switched. You compose F on the right by that disk automorphism that maps 0 to Wm. In other words, you compose with the inverse of psi sub Zm. So you have psi sub Zm composed on the right. So psi sub Zm followed by this F, followed by that disk automorphism that maps W sub m to 0, and you'd be done. Okay, so if an F that does this exists, then there is an F tilde that does what I indicated will exist according to the description I gave you. You compose on the left and you compose on the right by appropriate automorphisms, and you can now see how this is reversible. If you have an F tilde that interpolates this, then you compose with automorphisms on the left and the right in the reverse order. Now this is the hard part. This F tilde, so now see what happened. At the cost of complicating the appearance of the first n-1 pairs, I have changed the last pair of points. I have transformed my problem to an interpolation problem where the last pair of points is 0, 0. Now there exists an F tilde that interpolates what I just wrote, if and only if there exists another map F dot that interpolates this data. Now, this is a hell of a lot more complicated looking in the following way. All the first entries remain the same as before, but every entry upstairs, every psi sub wm of wj is divided by psi sub wm acting on zj. So the question will immediately arise, how come this is not 0? This is where the fact that z1 through zm are distinct is very, very important. z1 through zm are distinct. So when psi sub zm maps zm to the origin, because psi sub zm is an automorphism, z sub m is the only point that's going to be mapped to 0. So by distinctness, this that I have highlighted will never be 0. And similarly, all psi sub zm's acting on zj's will also never be 0. And the reason this ratio will be modulus of this ratio will be less than or equal to 1 is because of the Schwarz lemma again, right? Psi, this is well, not the Schwarz lemma, but the Schwarz-Pick lemma, sorry, by the Schwarz-Pick lemma. So you see, this term on the right is precisely, this term on the right is actually precisely psi sub z1 applied to z2. And the Schwarz-Pick lemma says that psi sub w1 applied to w2 is going to be less than or equal. And so that ratio is going to be less than or equal to 1. Just replace what I showed you just now. Replace z sub m by z sub 1 and replace z sub 2 by an arbitrary zj. Okay. But what this does is, do you see? This is an interpolation problem where there's one fewer pair. Instead of an interpolation problem that is going to match m distinct points to m designated points, this maps m-1 distinct points to m-1 designated points. And the designated points are kind of ugly looking, but now how does one prove this? Here I'm going to be kind of rapid. Do you see that because of where this point is mapped to, so you see what I have is I have psi sub wm acting on a w sub j divided by whatever is the corresponding z entry. So you see, I have no choice. If f dot has to exist, it'll have to be f dot z mapping z inverse to f tilde of z, which is totally well defined away from 0. But how do we know this is well defined? In fact, we will show that f dot is not just well-defined at 0, but it gives us a holomorphic function. And as you can see, since there is a problem only at an isolated point, which if it were a problem would be a pole, I just want to show this is not a pole. So I will use the Riemann removable singularity theorem. And I'm again going to use the Schwarz lemma. So you see, f tilde is given to be an interpolant. So by Schwarz lemma, mod of f tilde of z divided by mod of z is less than or equal to 1. I'm just taking phi equal to f tilde over here, right? But do you see what I have just highlighted is the modulus of this quantity away from 0. And so this function is bounded in a deleted neighborhood of 0, and by Riemann's removable singularity theorem, this is at least holomorphic. But the question is, why does this take values in the closure of the open unit disk? I still have to show that. Without that, I am not done. And I am simply going to say, actually, this above inequality, if I manipulate terms, I get this. And to those who remember the proof of the Schwarz lemma, this Schwarz lemma, we'll see how that same trick tells us that f dot also belongs to the class B. But I am not going to clarify anymore. I simply want to, for completeness sake, I am saying that this if and only if can be fully justified. I want to move on because I want to get back to the linear algebra part of it. But to motivate the linear algebra, I now need a picture. And the reason I'm actually presenting on slides is because I don't know how to fit this picture on the blackboard. So you see, this deflation trick reduces our problem to that of characterizing the existence of a certain two-point interpolant, which is, if the existence of an interpolant for the data that has been given to you is equivalent to the existence of an interpolant for an associated problem when there is one fewer pair. Instead of m pairs, there are now m minus 1 pairs. You apply the deflation trick again and again and again. And at the end, this data would determine a pair of Z1, a pair of Z's and W's for which you are reduced to determining whether or not there is an interpolant, which of course you know how to do, right? So that's how the deflation trick works. And I am now going to actually take motivation from this deflation trick to solve an associated linear algebra problem, a sequence of equivalences of positive semi-definiteness of quadratic forms, and that will deliver the proof. Okay, so now there are these complicated looking things over here. Let me just define what they are. So Z sub 0, Z0 sub j is nothing but the jth datum I have been given here. And W, there is a typographical error here. I should have a subscript that I have forgotten. So when I post these notes, I'll have to remember to correct this error. So Z0 sub j is the jth datum, is the jth W datum given here. And you see these double suffix things are whatever we saw in the previous slide under this second deflationary step. So we actually write down each of these data inductively. So let's just look at how we get Z upper 1 sub j from Zj. So Zj, remember, is Z0 sub j, right? So how we get Z1 sub j is what we did over here, okay? We apply psi sub Zm to Zj, and that's exactly what this formula is telling me. So if k, so I want Z1 sub j, that means I have to take k equal to 0. So I am applying psi sub Zm minus 0, which is Zm. The reason I have this in blue is, I got my colors reversed. So I have this color scheme to tell us that this is nothing but the Z datum of the last pair before I perform a deflation. Now here, I will again, on the W side, I will apply to each W sub j. So let's see what W1 sub j looks like. So I'll have to take k to be 0. And this ratio I have is what faithfully reproduces what you saw in the previous slide. And this parameter k comes in because from Z1, Z2, dot, 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 Zm, W1, W2, dot, 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 Wm, when you get Z11, Z12, dot, 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 and ZW11, W2, dot, dot, dot. If you apply the deflation to this latter, then this generalizes the formula you would have to use. Okay. So now, so I have this picture now. You see, in the previous picture, I had the sequence of implications. And but you see, each of these implications is actually an equivalence. So in this picture, I'm going to reverse this arrow. I'm going to go around the circle this way. And then what I'm going to complete the circle is by showing that this interpolant implies a positivity condition of some matrix, which will imply the positivity condition of a smaller matrix, which will imply the positivity condition of an even smaller matrix, and ultimately this, and that this implies this particular implication that I am highlighting, we have already proved. So that is how this proof is going to go. But actually, I'm now going to completely switch gears and just jump this whole problem and look at a problem on quadratic forms. So all of this was really a motivation for a problem on quadratic forms. Because kindly note, I said that to motivate the problem on quadratic forms, so I have this particular implication, but it's actually an if and only if. I have this particular implication, but it's actually an if and only if. But for the point of view of the schematic, I have shown my arrows going this way. And I will have finished the proof of the Pick Neven-Linna problem if I had a sequence of implications going from this assertion, linking up to this positive semi-definiteness statement, right? But actually what I will show is that the implications that I need to prove, they are actually equivalences. So I will have, on the one hand, a set of complex analytic equivalences, and I will show a sequence of linear algebraic equivalences. And since everything is linked by an equivalence, we will have each of the statements that you see is equivalent to every other statement that you see, but in particular, this statement is equivalent to the positivity of the m by m matrix we are going to establish. Okay, so the way I'm going to do this, I'm going to completely forget about the data coming from a disk. I'm just going to take, so that's why I'm going to do a change of notation. I'm going to take a bunch of points, little a1 through little a, and these don't have anything to do with the data of the interpolation problems. They're just placeholders. Let these be distinct points D, and let B1 through Bn be not necessarily distinct points, but repeated according to multiplicity, also in D. So consider the two Hermitian forms. So you see, this form is precisely the Hermitian form induced by this Hermitian matrix. So that is where this form is coming from. Now, this is an associated form, and it is a form that has associated with it an n-1 times n-1 Hermitian matrix, okay? And where this form is coming from, this is coming from the deflation trick, right? Because wherever I see an AJ, I'm replacing it by psi sub an applied to AJ. And wherever I see a BJ, I'm doing something more complicated. I am first applying B sub n to each BJ, but then I am again dividing by this guy that I told you about. And you also know why this is not going to be zero. This is not going to be zero because of the distinctness of these ANs. So the motivation for why I want to look at these two Hermitian forms is clear. Now, I want to actually say that it just suffices to prove that the Hermitian form H, A1 through AN, B1 through BN, this Hermitian form is positive semi-definite if and only if the second Hermitian form H tilde of A1 through AN and B1 through BN is positive semi-definiteness. But at this stage, you might want to say, but why so? You just said 2 minutes back that I have established that this 2 by 2 matrix, its positivity implies the interpolation of an auxiliary 2 by 2 interpolation problem the existence of an interpolant is equivalent to the problem we are really interested in. So there is a bunch of equivalences of positive definiteness of Hermitian matrices of size m by m, m-1 by m-1, m-2 by m-2 that I said 5 minutes ago I need to establish. So I need to establish basically the equivalence of the positive definiteness of an m by m Hermitian matrix and an associated m-1 times m-1 Hermitian matrix. And then I want to show the equivalence of the positive definiteness of the latter matrix with an even smaller matrix and so on. So why is this enough, you will ask? Why is this enough? To see why, so now we look at our complex analytic problem. This is where M was used. So remember, if I have 2 pairs of points, my problem is solved. My theorem is proved. What I'm interested in is when capital M is bigger than 2. So you see, in this previous picture, I need to establish m-2 equivalences. And these are equivalences between a square matrix, the equivalences between the positive definiteness of a square matrix and the positive definiteness of a different square matrix of smaller size. Aha, so you see, this is why I used capital N here. So let's agree, we need to establish m-2 equivalences. So in this sequence of equivalences that I need to establish the ith equivalence, we will simply In this statement that I claim it suffices to prove, in this we will take capital M to be, capital N to be, so this is N for new, to be equal to M for Maharashtra, M minus I plus 1. So you see the first equivalence. So what is the first equivalence? The first equivalence will be the equivalence of the positive semi-definiteness of the M by N matrix with a matrix that is one step smaller. And if I show that equivalence, then maybe step by step, I can get down to showing equivalence with the positive semi-definiteness of this one. So what is the first equivalence? The first equivalence, we take capital N to be M minus 1 plus 1. In other words, we take capital N to be M, which is exactly what we want to do. The first equivalence involves an M by M matrix. And so the A's that I see up here will be replaced by these numbers. So for the first equivalence, I is equal to 1. So this superscript is 0, and I have nothing but Z1 through Zm. And these B1 through Bn are nothing but W1 through Wm. Having then established an equivalence with a matrix whose size is 1 smaller, what I do is I reapply this equivalence, but I now take N to be, this is the second equivalence, N to be M minus 2 plus 1, which is M minus 1, and then my A's will change and my B's will change. So you see, this is a very cleverly selected form with placeholders. And these placeholders are the A's and the B's, and that's why I use A's and B's and not Z's and W's. So now we just do a computation. So this A super 1, AJ super 1, and AK super 1, they mean the same thing that you had seen before, which is I'm going to AJ super 1 is the application of psi sub, in the complex analysis problem, it was psi sub Zm. In this auxiliary problem, it's psi sub A capital N. So this A1 sub J, I have marked in green. What it is the corresponding thing in green over here. And similarly, this A sub K super 1, it is the stuff that I have marked in purple. So the colors are matching. So this is an easy calculation. The thing on the left is easy computation, is this thing on the right. But now what happens is when you have these things in the denominator. So when you take a common denominator, you actually get this. And when you simplify the numerator, this thing, there's a term like this that factors out and cancels out, and you get this. And so there'll be a similar computation for 1 minus bj square bracket 1, bk square bracket 1. Notice I'm not using round bracket over here because bj round bracket 1 has a meaning that comes from my complex analysis problem. So bj square bracket 1 is simply, you take bj and you apply to it psi sub b sub n. So it's exactly like this. So a similar computation will give you this equality. So you see, this is the jkth term of a certain Hermitian form. It is given in terms of a certain product. So you see, if I now look at this new Hermitian matrix, or I look at the resolution of the quadratic form that is engendered by the Hermitian matrix whose jkth term is this, then just arithmetic gives me this term. But remember this ratio that I have, this is important to remember. This ratio is the entry in the jkth entry of the Hermitian matrix that determines the first Hermitian form, the H form, not the H tilde form, but the H form. And so you see, given this identity which comes from this computation, we have that the Hermitian form H with A1 replaced by this, A2 replaced by A1 sub 2, A3 replaced by A1 sub 3, and so on, and AN replaced by 0. Now the B1 is replaced by B square bracket 1, okay? It's not B round bracket 1 because B round bracket 1 has a slightly different meaning, which we shall see in another 3 minutes from now. So I have the H form, but in the placeholders, I put in these different, in place of the variables, I now put in these entries. Notice the last entry becomes 0. The last entry for my A's is 0 and the last entries is 0. So the Hermitian form H with these new substitutions is simply the old Hermitian form. Remember, the old Hermitian form is engendered by a Hermitian matrix whose jkth term is what I just highlighted. So this is the old Hermitian form acting not on the vector psi, but on the vector, this diagonal matrix acting on the psi. So this is what we have achieved. We have achieved that the original Hermitian form is positive semi-definite if and only if the original Hermitian form, but the placeholders substituted by these entries is positive semi-definite, which doesn't solve the problem that we are interested in, but this implication actually places us in a position to now attack a purely linear algebraic problem. At this point, I am now going to forget about round brackets, square brackets, and so on and so on. So I'm going to define a new form. This is the form, I'm going to call it H tilde. And just to say that I'm starting afresh, I'm going to have my parameters be given by capital A's and capital B's. Now the motivation of this form should be clear. You see, if for each Bj, I take B square bracket 1, you see, Bj, capital Bj divided by so let me repeat again. If for each Bj I substitute B square bracket 1 sub j, and for each Aj, if I substitute A round bracket 1 sub j, then you see big Bj over Aj is actually the thing that I need. This is the reason why I had used square brackets over here, because I want to indicate that this jkth entry of a certain matrix is that of an intermediate matrix and not the one that I want, which is over here. This differs from the matrix that I want by a division, and that is given by this quadratic, this new, much cleaner looking quadratic form. Okay. So you see, in view of what the H tilde form is, which I just showed you, we would be done if I could show that the H quadratic form with A1 through AN, where the nth term is actually 0, and capital 1 B1 through capital Bn with the last term 0, is equivalent to the positive semi-definiteness of the H hat form that I had just now introduced. And I must point out to you, with all the other parameters being non-zero. This is the stipulation that bears connection with the complex analysis problem, which is, in the complex analysis problem, we have this feature that the thing that we are dividing by is always non-zero. That stipulation is being carried over here. So we have now two very, very clean forms. There are no psi's and there are no reciprocals of psi's. We just have to compute. Now, I must point out that this class of Hermitian forms actually occurs a lot in the theory of quadratic forms. And that's what I meant by the remainder of the proof is just, I am lifting a proof that comes from this broader theory of quadratic forms. So we compute. This form, it is equal to, so when I look at the Hermitian form that this matrix or the matrix underlying this form engenders, I will get psi sub n mod squared. I'll get a bunch of terms. Let us even see how these terms come about. Let's again go and look at this H. Let's again go and look at this H. This is the guy I'm looking at. So you see, when J and K are both equal to N, then remember the last term is 0. Capital, in this place where I have a capital A and I have to enter a 0, this place where you see a capital B and I have to enter a 0. So the numerator is actually, when both J and K are equal to N, the numerator is 1, the denominator is 1. Now let's look at the extreme right column and let's look at the bottom row. Okay. In that case, what happens is, again, if I'm looking at the extreme right column, then K is equal to N, where I am substituting a 0. So again, you see this entry just becomes a 1. And similarly, when I look at the bottom row, for the similar reason, the bottom row is just a row of 1s. And that's where these terms are coming from. And then I have a bunch of other terms. I'm not writing them now because you're going to see them in the next step. So what I'm now doing is I'm completing the square. Again, a very standard move in the theory of quadratic forms. So when I complete the square, these other terms now show up. There is the specific n-1 times n-1 Hermitian matrix that engenders this Hermitian form. And now we have a really easy calculation. So this red thing, remember, is the thing I'm carrying over from the previous slide. So now let's compute. 1 minus bj times bk conjugate divided by 1 minus aj ak conjugate. The whole thing minus 1. Well, I just take the common denominator, 1 minus aj times aj conjugate. So when I take the common denominator, the numerator simplifies this way. And then what I'm going to do is, so remember, I had told you all of the other parameters are non-zero. So all my a's are non-zero. So I can divide through by aj times ak conjugate, which gives me 1 minus the ratio of bj and aj times the conjugate of the ratio of bk times ak. The denominator remains the same. And then, of course, if I've taken aj, if I've divided through by aj ak conjugate, I must also multiply so as not to change the equality. So I have this. And so I have this identity. The quadratic form with these entries is equal to this interesting looking term, which I obtained by completing the square. And simply so remember, this is in fact the JKF entry of the Hermitian matrix I'm interested in, except that it's messed up by this factor. But when I look at the quadratic form that it engenders, it is h hat applied to the diagonal of a1 through a sub n minus 1 applied to psi dash. What is psi dash? I'm just representing the vector psi by psi dash comma psi n. So there's a typo here. This should have been psi capital N. So we have this. So you see, we are done. Because in one direction, if this is positive semi-definite, then this is certainly positive semi-definite. But if I assume that this guy is positive semi-definite, from this I have to infer that only this thing is positive semi-definite. But then the way I do it is I apply this, I evaluate this quadratic form at the vector psi 1 over a1 dot 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 psi sub a n minus 1 divided by a sub n minus 1. And in the last entry, I'm going to put this. So do you see what's going to happen? When I input, I don't know what just happened. If I input this quantity over here, I input what I am supposed to substitute here, I just get a huge big 0. And these psi 1 divided by a1, psi sub n1 divided by a sub n1, when I input it over here, the diagonal matrix applied to this term simply tunes out everything that I'm not interested in and leaves just this matrix untouched. But if this quadratic form is non-negative definite, that implies that this quadratic form is non-negative definite. But that was exactly the last statement that I had said it suffices for us to prove. This is the statement dagger, right? I must say that in the slide, I didn't spell out the converse direction. I said, if we assume this is positive, semi-definite, etc., etc., the converse is trivial, because if this quadratic form is positive, semi-definite, I'm adding on to it a positive term. So each quadratic form will be positive definite, positive semi-definite. That's what I meant by this is just the statement dagger. And so you see, if you cast your mind back to that diagram, we are done. So that proves the Pick-Neven-Liner theorem. But do you see what happened? We sort of had a sequence of equivalences given by complex analysis, namely the deflation trick. That actually guided the choice of parameters that we must need to substitute into a quadratic form that sets the ball rolling. And what we did is we actually proved a completely parallel sequences of equivalences in the realm of quadratic forms. So there is this intimate connection between these quadratic forms and these interpolation problems. And with those words, I'm finished with the lecture part of it. Any really quick questions? I'm already 3 minutes above time. So maybe let's just take one really, really quick question, if anyone has any. No.